Okay, so we're continuing with week 9, and there are indeed 9 of you here. It's getting worse every week. I swear, by the end of this course, I'm probably going to have a lecture where no one turns up. But as far as I can tell, you are watching the videos from home, so at least that's some consolation. I do like it when you turn up, though, by the way. It's nice to have someone to engage with. Anyway, so on Monday we were talking a bit about collision. And the main thing I wanted to establish there is there are kind of two sides to the collision problem. One is detecting collisions, which is just the geometry of do these shapes overlap, literally as geometry calculations. And then the second one is how you handle them, which is a combination of having strategies like move back to your previous position, which we try and make sure is always a safe thing to do by updating one at a time. 10, hooray! So you move back to the previous position and then you do something to prevent the collision from occurring. And that's in proper games, what you would do there is you apply an impulse, and the effect of the impulse is to change the velocities of things so that they move away instead of moving towards each other. And in our kind of simple games, you do that by flipping the y component of your velocity or whatever it might be, has the same effect. It makes things move apart. So that's basically what collision's all about. But it turns out there's another big important thing about collision that you have to do, and that's all related to issues of efficiency, actually, which are quite important. And it turns out, to deal with that, you need to think about something called spatial data structures. So that's what we're talking about today. Just let me check something on my watch. Okay. Yes, that's what I said. We've looked at the basics of doing collisions. Fine. So remember, we decided to move the entities one at a time rather than moving them simultaneously. The reason for that is that if you move them one at a time, you've always got somewhere to go back to if you get stuck. And it turns out that's a useful escape hatch. But there is the question as to, okay, you're checking your entities for colliding with each other, but exactly how many entities are there and how are you performing those checks? So the idea is that if you didn't have any special knowledge and you had a totally general system with a bunch of objects in it that were all independent and were kind of moving about and doing stuff, then every time one of those moves, it could potentially collide with any of the other objects in your whole game, couldn't it? So in theory, you have to check against every one of those. So imagine you've got like 100 things in your game that are all moving about. It's like, well, every time one of those moves, it has to do a collision check against the 99 other objects. Because it could be any one of those that it's bumped into, and without extra information, you don't know which, if any, it's collided with, right? So you just have to. But that'll hopefully ring some bells. If I tell you that every object has to check against every other object, what does that make you think in terms of computational complexity?
I think there's a world as an array and all we check.
No, shut up. What does it make you think about the order of complexity of the collision operation? You say?
N squared.
N squared, correct. Brilliant, right. So because everything is having to check against everything, that's the classic definition of an n squared complexity problem, right? Oh no, when I see n squared, I think, oh no, because n squared is quite bad, right, in terms of performance. You know how it works. It's like 100 things, then 100 times 100, so that's 1, 2, 3, 4, 10,000 operations to do. It's tolerable. But let's say you've got 1,000 things. You get 1,000 things, n squared is 1,000,000. And this gets bad quickly, right? The classic thing, of course, if you just want to think in your head about an n squared problem, is if you double n, then the number of operations you have to do becomes 4 times bigger. So you put twice as much stuff in your game, and it's now 4 times slower. And it's like, well, that's quite annoying, isn't it? And it doesn't take long before that bad scaling becomes a real problem. So you'll find, like in a real game nowadays, you easily could have thousands of entities. So that's potentially millions of pairwise collision comparisons, and that's going to get too slow. Now, so this check everything against everything is a problem that we've actually slightly solved already by using some tricks. When I was talking about terrain on Monday, I said that one of the tricks that terrain systems use is they put the terrain on a regular grid. And that way, among other things, instead of having to check against every triangle on the terrain, of which there are very many, you just very quickly find out which part of the terrain grid you're on, and you only collision check against the triangles that are basically in that grid square and in the ones immediately around it, which is a very small number. So you're now only checking against like half a dozen triangles. And that's brilliant, right? You've gone from checking against potentially millions of terrain polygons that you might have been colliding with, and you can in fact use the grid to say, nope, I know I'm only going to be colliding with these 2 or 3 here. So that's a great technique. So that's what you do. So the entity that's moving, you can use its coordinates to kind of index into your kind of array for the static grid, and you get to the answer really quickly. So imagine you had n objects again moving, but instead of thinking about them colliding with each other, think about them colliding with the terrain. So imagine you've got like 1,000 objects and the terrain's got like 1,000,000 polys in it or something like that. Well, you go from having 1,000 times 1,000,000 to having just 1,000 times a very small number. You just instantly know which terrain tiles are the relevant ones. So what that basically does is it becomes an order n operation. It means that if you had twice as many objects, you would just have twice as much work to do. Right? It scales linearly, and it's hard to see how you can do much better than that. Right? I mean, obviously, it'd be nice if you could, but unless you do some like extreme magic, basically, if you put twice as many things in your game, it's going to be at least twice as slow, because it's like those things have to do some work, right? So if you can, by using a terrain grid, you actually get that. You get linear behavior. So you put twice as many things in, and it's only twice as slow. It's not 4 times as slow. So ON is pretty good. ON is okay. And it would be nice if we could make everything be like ON. The problem, though, is that we've got these other objects that are moving around freely. They're not constrained to a grid. They're just like, they're cars and vehicles and missiles and characters and animals, whatever they might be. And they're all wandering around doing their own thing. So they aren't rigidly aligned to some kind of magic grid system. Therefore, you don't really know where they are. Therefore, you have to check them all against each other, and you're back to having to do n squared complexity, which is bad, right? And this happened in GTA early on. When they started developing GTA, it was just written so that when every object moved, it just did a collision check against like all the lists of all the other objects. And to begin with, that was okay because we had small maps. It was only like the city was only like 4 screens long, and you only had half a dozen cars or something like that. So it didn't matter if those half dozen cars were collision checking against each other on every frame. It was fast enough. But as the game developed and we realised that it was good to have the cities be large, which they were always planned to be, but it takes time before the level designers build them and before you get all the art content. So as the city started to get big, where it's like hundreds of screens long, and you've now got hundreds of vehicles in the system, and now you've got 100 times 100 collision checks, and you put pedestrians in, and they're also having to collision check against each other and the vehicles. Guess what? It got really bloody slow. So same problem. And it's a problem that would have been solved in the terrain case by having the magic of a grid, or in the case of breakout, you can solve it the sort of similar way where the breakout wall does the same trick. It uses brick coordinates, so it knows which brick to worry about. You didn't have to write a loop that iterated through every brick. But again, that's because you had this kind of grid trick. So if only we could do that with our dynamic objects, these things that are actually moving about in the world, if only we could somehow constrain them to a grid. So let's just do that then, right? Make them be constrained to a grid. It doesn't happen for free because by their very nature, a general object can in fact be anywhere. So it can be any position, any XY coordinate. So it isn't just a case of like with the bricks where you knew that the brick at position 3 down 2 across was always at 3 down 2 across and could always be found there. It's like now they're all moving now. So there's some work to do to track where they're actually going. But the idea is that you can still do this, and you pay a small cost track where things are on the map, but you get the benefit of being able to put them into a kind of imaginary grid, and then once you do that, you can make your collisions faster. So this is the kind of thing you would do. So you've got a bunch of guys who are free to move anywhere they wish, as whatever their update logic tells them to do, but we impose like an invisible grid on it. And you can see these dotted lines are the kind of magical invisible grid that we're sticking on it. And all we do is, whenever somebody moves, we have to keep track of which grid square they're in. And then what that means is, when it's time to do your collisions, you only really need to worry about the other people who are in your own grid square, or maybe your grid square and its neighbours, depending on how you do it. And this is great because instead of having 1, 2, 3, 4, 5 guys, each of which would have to collision check against 4 other guys, that'd be 20 pairwise comparisons. Instead, what you do is, this guy, well, he just says, well, there's nobody near me, so obviously I don't collide with anyone. Done. Same with him, same with him. These ones is like, oh, there's one person who I might be bumping into because he's in the same grid cell as me. So you do one collision check, and so does the other one reciprocally, right? So we're down here to like, we did 2 collision checks, whereas previously we'd have had to have done 20. So this is like a great saving if you can do it. The problem is, in order to do it, you need to know which grid cell everyone's in. But that's okay. The idea is that just you make it so that whenever an object moves, one of the extra things it has to do is it has to do a little calculation to say, oh, by the way, which grid square am I in? And you remember that somewhere. So that's quite a good idea. So I gave you a very simplified version of it there, where the guy was like only checking with things that were in his own square. But actually what you have to do is you have to say, you work out where I was and where I'm going, and you kind of create like a little bounding volume between your past position and your future position. And then you say, now, that volume, which parts of the grid does that intersect? And that might be more than one square sometimes. You know, if you're moving from the boundary of one square to the next one, it kind of stretches along it, and you end up having to check against 2 cells, or maybe even 4 if you're at the, if you're at the corner of the grid. It might be that you end up saying, okay, I'll actually check against 4 grid squares, but that's still only a small fraction of your total map, so it's still a good saving. So there you go. So in order to do this, though, you have to go to track positions. That's just what I said. So you have to do a little bit of recomputation, but the whole idea is that the cost of computing these grids is basically a linear thing. You know, it's every object does what it was normally doing, and then does and where am I in the grid? And that's a simple operation, and it's just times n. You know, every object does that, so it's still a linear scaling thing. And that's a good trade-off. I'd rather have this linear cost of working out where I am rather than the n squared cost of having everyone compare with everyone. But one consequence of this is, if you're going to track the positions in an imaginary grid, you can't just go around changing the positions of your objects like whenever you like without doing any extra work. You can't just go in and do .x equals something else, because if you go and change the x position, the problem is the collision system needs to know which grid you're in, and you might have changed every time you touch your coordinate. You might have changed, so you can't really just muck around with your coordinates. But that's kind of okay, right? Because an object's coordinates are supposed to be like private internal data anyway. Really, other objects shouldn't be mucking around with your x and y positions. They're your business. So stuff like this, where you take some entity and you change its x position, is actually stuff that you generally shouldn't really be doing anyway. So what you do instead is you have a kind of like an access function, for updating these things, like a setter, yeah. And the idea is that the setter function gets called to update the position, and it just does 2 things. Not only does it update the position, it also checks whether what grid cell you now belong to, and it might be the same one you were in before, but it might have moved you to a different one. So that update routine would then say, oh, he's in a different part of the grid, by the way. And of course, if you don't do that, the problem is you get phantom objects, that the grid thinks they're over here, but they've moved over here. So now they don't collide with things because the thing doesn't know. But as long as you do it the right way, you can make it so that whenever you change the position, you kind of automatically update the collision grid, and then it all just works. At least that's one way of doing it. Okay, so that's it. You can build grid tracking into the update routine. So having done all that, so we've kind of come up with this idea that, yeah, if we had a grid, it would be good. It would let us get, a much reduced collision complexity, but we still have to do it. And often the solution with these things in games is you create a manager object that has to be in charge of this thing. We created the entity manager to deal with the hassle of creating and updating and rendering all the things. Remember early on, when you added a new object, you had to go into the update simulation routine and add a call to it explicitly, and you had to add one in the render as well, and you had to do all this nonsense. And we changed that so that now what you do is you just register yourself with the entity manager, and the entity manager handles the chores of updating you and rendering you, just does it for you. Same sort of thing with collision, where you use a spatial manager that is in charge of this data structure thing. So there we go, right? We'll have a spatial manager. And the code for this is fairly easy. What it means is you do something like this. So let's just start by looking at the update routine of a thing, right? So generally the way we've had it up till now is the update routine would do something like, it would cause some calculations, it would update the position. This is where you calculate the force. Well, if you take the spaceship, this is the bit where you'd say, am I pressing thrust? Is gravity on? What's my average velocity? Compute the new thing, compute the new position, blah, blah, blah. All that stuff would be in there. Well, what I'm suggesting is that all we need to do now is, before we start that, we're actually going to remove ourselves from the Spatial Manager. This is a little bit of a trick. By removing yourself from the Spatial Manager, well, basically it's because we do it symmetrically. We remove yourself from the Spatial Manager, then when we move you, we put you back in. So the important thing is, by registering with the Spatial Manager after you've moved, that's what keeps track of your current position. If you've moved to a new position in the grid, this is the thing that will realise you're in the new position. But maybe that position was different from your previous one, and you have to kind of erase your old position. So we do that here. We basically take you out of the grid. So imagine you're in this tile here. We just take you out, and then we work out what your motion was. And maybe you're still in the same grid square, maybe you're not, maybe you moved to a different one. And then at the end, we put you back in. And that way, this system tracks where you are all the time. This isn't the only way of doing it, but it's quite a nice one. It's also got the nice advantage that you remove yourself from the grid before you start all your movement logic. One side effect of that is it means you don't collide with yourself. If you stay in the grid and you get to the point where you do a collision check against all the objects that are in your grid squares, one of those objects would be you, and you have to write some special case stuff to not collide with yourself. But because I've gone with this idea of taking you out in order to clean it up, it means that you can't collide with yourself because you've been taken out of the system while you're moving. Right? So that's basically what we do. We just take you out and put you back in. There's a little bit of work involved in doing this. In the system that I've come up with, the idea is that in order to talk to the Spatial Manager, you need to have a way of letting the Spatial Manager quickly update its data structures about the entities. And I've decided that a good way of doing that is to give every object a unique spatial ID that can be used to track them. It just turns out a fairly easy way of doing it. So we have this thing where when we initialize all our entities now, we ask the Spatial Manager, could you give me a new ID? This is like I've created a new object, please give me a new ID. And the way I've done it is it's just a numerical ID. The first guy's 1, the next guy's 2, 3, 4. We just keep counting up. Very simple, right? But it means they've all got unique IDs. The reason for having the unique IDs is it makes it fast for the Spatial Manager to look things up when it's adding and removing them. So you just do that, and then there's a little bit of extra work you have to do. The Spatial Manager's job is to store the collision volumes as they would be, right? To track the kind of collision shell around the object. In order to do that, it needs to be able to say to the entity, well, what is your collision shell? So we're just going to use a fairly simple system where our collisions are circle-based. So in that case, all you really need to do is be able to get the position of the object, which is going to be the XY centre of the collision circle. And there's actually a bit that I haven't specified here where you get the radius as well. And you can extract the spatial ID. So the spatial ID is just a piece of interface glue that allows the entities to talk to the Spatial Manager. And there are other ways you could have done it, but this is an easy one, so it's the one I'm showing you. Right. So the other problem that comes up with collision systems is that depending on the relative size of your grid and your objects, sometimes you get objects that are in multiple cells at the same time. You have simple cases like this one, like this circle is an object and he's only inside one grid cell, so it's kind of easy. If you say, which cell do you register in, you register in that one, you're done. But you look at ones like this guy here, who is overlapping on 2 or maybe even 3 cells at the same time, or this one who's definitely overlapping with 4. Basically, there are 2 fundamental answers to this problem. One is you say that, okay, if I'm overlapping so that I happen to be touching 4 cells, I need to register in all 4 so that you tell the Spatial Data Manager, I'm here, I'm here, I'm here. That way, if there's someone in here, they know that when they do the collision check, they include you because you've kind of spread yourself out to every cell that you touch. So that way, the code here would say, okay, I've got this guy and this guy are both touching this cell, so you would include them. So that's one way of doing it. The other way of doing it is to say, no, I'll only register myself where my center point is. So this guy here would say, I'd only register in this cell here. But that means he isn't listed in this cell. And of course, he can obviously bump into things that are in this cell, right? So if you do it that way, where you register in one cell, it means that when you're doing the collision check over here, you have to check the boundary cells as well, obviously, right? you understand that? There are two ways of doing it. You can like register on every cell that you touch, or you can register just in one cell, your home cell, but that means that when you do the collision search, you have to do it like one cell wider than you would have otherwise done. So you end up having to search in a kind of a 3x3 grid. Yeah? So both of those are reasonable solutions. I slightly prefer the second one because it's simpler to only ever have to register self at one position. One of the things is that it means that the memory usage is constant. Like if you're in a real system where you have to worry about your exact memory allocations, if you do it where you only register in one place, it means you know up front that every object requires the same amount of space in the spatial manager as every other object, and it does so all the time. Whereas if you do the multiple registering, it means that sometimes you register in one place and sometimes you register in 4, which means your worst case memory usage is 4 times more than your best case. And like in consoles where memory allocation is a big pain and you don't want to have these, you wouldn't want to have to allocate 4 times more memory than you need just in case everybody ended up standing at the corners, right? You don't want that. So I tend to go for just register in one place so that it's constant memory usage, and I'll pay the price of having to search over a slightly broader area when I'm doing my collision checks. So that's what I tend to do. So this is my preference, just lock the center point. It's also easier to code it this way. You don't have to worry about how many squares am I in. You just use my center point and put me there. Yeah, so you just handle it by making the footprint a little bit larger to compensate for that effect. And as long as you don't have objects whose radius is actually bigger than a grid cell, then you only need to do it by one cell. And you just tend to have a rule. You tend to not let your game objects be bigger than a collision cell, because if they get bigger than a collision cell, they can potentially be overlapping on like 9 other squares, and then it just becomes really annoying. So you don't do it, and if you've got really huge objects, you break them up. Like sometimes if you've got like a big, like a huge vehicle or something like that in a game, it's actually internally segmented into a couple of separate objects so that each one of those objects is smaller than the collision cells, so that you don't have to worry about this weird stuff. All right. So the cool thing is, if you do this and you track the positions and you put them in a grid, you definitely reduce the number of collision checks that you'd have to do by quite a good margin, and that's what we want. So that's great. But it's worth thinking analytically, like what does this do to the actual order of complexity, right? Well, by putting a grid on, imagine you put you pose a 10 by 10 grid on your world, right? Then that means, and imagine you have 100 entities. So instead of having 100 entities that are having to collision check against 100 entities, you have 100 entities, each of which is only really having to worry about the neighbour in its own cell, and each cell is, is 10 by 10, so each cell is 100th of the whole map. So on average, there's only one other person there. So now it becomes, 100 things, each having to compare against basically one other thing, right? You understand? Yeah. So it reduces the number of collision checks basically by the number of cells that you put in your grid. So you put 100 cells in your grid, you've reduced your collision checks by 100. That's really good, right? But it's still technically n squared, because that's how all the complexity order works, right? Because you say we've gone from n squared to n squared divided by 100. Divided by 100 is good, but it's still n squared. It still means if you doubled the number of things that there were in the world, you'd have twice as many things, you'd have 200 things now, and each cell would be twice as dense because there are twice as many things. So each cell would have 2 things in it now. So now it would be 200 times 2, so it would be 400, right? And previously it was 100. So we're back to the same problem. We doubled the number of things in our world, but we end up having 4 times as much work to do. It's still 100 times better than it was before, but as I say, 100 is only a linear saving. So the fact is that although the grid system is really good, it's still n squared complexity. It still doesn't scale brilliantly. You get like a one-off linear saving. But, by the time you get thousands of entities, you're kind of back in trouble again. So there you go. It's actually n squared, albeit a better one. So this is still not ideal because we still don't like n squared, even though it's better than it was. As I say, you double the number of objects, you've still got 4 times as much work to do. So the trick to that is, imagine you put twice as many entities in, which is giving you 4 times as much work to do. How do you compensate for that unwanted factor of 4? Well, really, the factor of 2 is almost unavoidable, right? Because it's twice as many things. You can't help that. but you got times 2 times 2. If only we could get rid of that other times 2 factor that was getting in the way. But how do we do that? Well, really, the only way you can do that is if you make the cells smaller. If you made the area of the cells half as much, then that would mean that the density of those cells would go back down from 2 to 1, right? So it would kind of compensate for the scaling of the world. So that's sort of the idea. The idea here is that as you put more and more things into the world, you can make your cells smaller. And you end up with a trade-off there. Like when you make the cells smaller, you've got more cells. And if you've got more cells, you need more memory to store them. So there is a memory trade-off here. But because the cells are smaller, each one of them's got fewer things in it. So you've got fewer things to collide against. So you end up kind of compensating for the bad performance scaling. And you see this a lot in computing and everything you do. You often get trade-offs, like you can, reduce CPU at the expense of increasing memory, or you can reduce memory at the expense of increasing CPU, which is one of these things that you balance. But the technique I'm talking about here, where you make the cells get smaller as the world gets denser, is a way of using a little bit of extra memory to save scaling on your performance. So there's the standard technique for this called a quadtree. You know what a quadtree is? Anybody? You do? Anybody else? Okay, the rest of you don't know what a quadtree is that true? Right, just not sure. Sometimes it's taught in data structures classes, but I guess you haven't encountered it yet. You know about binary trees though, don't you? Right, so a quadtree is basically the two-dimensional extension of a binary tree. So just to remind you, with a binary tree, and again, it's a good reference point, because the point of a binary tree is you had a big list of things and you wanted to search through them. The problem is that if you didn't know any better, you'd have to search through all n things. You're trying to look up someone's name in a database or something, right? And it's like, well, you'd have to kind of go through everybody until you eventually find their name, and that's kind of really slow, right? So the trick about the binary tree or a binary sort is if you put them in order, then of course you can say, is their name in the first half or the last half of the alphabet? And you kind of just jump to whichever half of the list is relevant, and then from there you jump to the next half and the next half, and you get very, very quickly to the end point. That's what a binary tree does. Well, a quadtree just does that in 2 dimensions. It does it in x and y. So here's the article from Wikipedia about it. You can maybe sort of see the idea of it here. So the idea is that you could start this thing with like one big grid, but the idea is you then break it up into quadrants, right? So there's like a totally black quadrant and there's a totally white quadrant, and here's a mixed one. So you take this mixed quadrant and you can break that down into 4 other sub-quadrants, and you just keep doing it that way. So it's like a factor of 4 decomposition. So for our purposes, what we're suggesting is that you could create a data structure where initially it was like one big grid cell, but as it gets more populated, it's got too many things in it, like above a certain threshold, you would break it down into like these 4 big quarter cells. And then as they get busy, you break them down into subcells, and you just keep doing it. So you can see here is that some parts of this are denser than others. That's because the parts that are dense have got objects in them, and you've decomposed those so that each cell has only got like 2 or 3 objects in it. And if ever a cell has got more than that number of objects, you say, please split yourself up into 4 cells. And conversely, if ever a cell has got less than some threshold, if it's only got 1 object in it, you say, fuse yourself with your neighbours and become big again. So it just dynamically changes the size of the cells. So that's what a quadtree does, and they're very often used in games. So the idea is that you've got this, the collision grid basically has an adaptive size where the cells are getting bigger or smaller based on how occupied they are. So this is great, this scales really well, and it works at runtime. So what happens is that if your game gets busier because you generate lots of objects, then the cells just automatically make themselves smaller, and that means you have fewer things to collide against, and it compensates for what would otherwise be causing you n-squared type slowdowns. They become just about linear. And this is good, so it means that even like a busier part of your map, you have a hectic part of the map, the cells there are made very small to deal with the fact that there's a lot going on, but the empty parts of the map have got kind of big empty cells that take less memory. So this is like a nice adapter trade-off. Because it's very general purpose, this is used a lot inside engines. A lot of the game engines, certainly Unreal, uses, well, not quite a quadtree, but for current purposes, we'll say it uses a quadtree, and it's quite a nice solution. So general purpose engines do this quite a lot. So here's the basic idea. Imagine if you had decided that your world was broken up into 4 collision cells, but you just generate a whole bunch of objects here. Like, somebody starts spawning out new things, you create new bad guys, or there's an explosion and lots of debris or something. So you get more objects, and this square ends up having, more than the threshold of, let's say, more than 4 objects inside it. At that point, you just say, okay, split yourself up, and then you create these smaller ones, and you keep doing that until no individual cell has got, more than, let's say, 4 in it. Which is really cool now, right? Because basically, if you can guarantee that no cell has got more than 4 things in it, whenever you update an object, that object just has to look at 4 things. Okay, and it has to look at the peripheral ones as well, so it's a bit more, right? It ends up being, you end up having to do the boundary. But the point is, it's only the order of like a dozen or so objects it has to collide against, no matter how busy your world is, pretty much. So that's quite a good trick. Okay, so again, I think this is just copied from the Wikipedia thing, scaled up. This is just to show you, like, these little points represent, objects that you're somehow storing in your quad tree, and the blue things are the actual cells that are encompassing them. So you can see it all just kind of adaptively. Like here, it's very busy and the cells get small, and here there's nothing in it, so the cells can be quite comparatively large. So this idea, the quad tree is the 2-dimensional analog of a binary tree. You take that into 3D, we end up with a thing called an octree. The quad tree becomes an octree because it's a quad tree with like another layer of depth behind it. So actually, 3D game engines is an octree that they use internally. And you can go and look at the Octree article if you want to know more about them. Right, so sort of same idea, you have like, so instead of I'm thinking the grid is a flat square, but in 3D it's a cube. It's a volume of space, and the cube would get decomposed into 1, 2, 3, 4, 5, 6, 7, 8 subcubes when it gets too busy, and each of those subcubes gets decomposed into 8 when they get too busy, and so on and so on. And that's how an octree works. So there's a little picture of an octree that's been decomposed around the classic bunny rabbit. Have you ever seen this bunny rabbit before? If you read like computer graphics papers, it's often used as an example object. If you go and look at videos in SIGGRAPH when they're doing like object deformation and stuff, you see that they tend to be throwing these bunnies at each other and watching them squish or turn their heads off or blowing them up. They're all doing terrible, cruel things to bunnies, but it's because it's a standard test object. And the idea here is that this object has been made to fill the space so that whenever it's occupying a volume, the voxel, by the way, this is what voxels are. Voxels are the cells within an octree, or at least that's one of the things they can be. If these individual cells are indeed called voxels, it stands for volume element. The vo is volume, so the same like pixel means picture element. A voxel is a volume element. So this is a kind of voxel decomposition, and again you can see that this part here is empty, so it's just one big simple voxel. But here where there's like a lot of detail in the ear, where it's very kind of fine, the voxels have to get small enough to handle the precision of it, so they just adaptively get smaller. So that's kind of how that works. Right, so that's all very fancy pants. And it's not the only one. Quadtrees and octrees are like the standard ones that you definitely need to know about. There are also things called Bsp trees. Has anyone heard of Bsp trees? How many have not heard of Bsp trees? Okay, most have not, right. So Bsp trees are really interesting. They used to be somewhat obscure, but they got made famous because, do you know who John Carmack is? John Carmack's the guy who made Doom and Quake and Wolfenstein, all those games. He's like a super genius guy. He used BSPs as the spatial database structure for Quake, and it's one of the reasons that Quake is as fast as it was. So the way BSP trees work is, I've been talking about like using like a grid structure and decomposing these axis-aligned grids. But if you think about Quake, where the dungeons are kind of angular and stuff, grids are not actually the ideal thing. So what happens in Quake is that each wall is basically a plane that slices the world in half. Binary, right? It slices the world into everything on the left of that wall and everything on the right of that wall. And then he takes the two halves on the left and right, and any of the walls in here split this part into two halves, and the walls in that part split into two. So every wall in Quake basically divides the whole world up into two halves in a recursive manner. So he actually creates like a tree structure defined by the walls, and it's called a binary spatial partition. And he didn't invent, Carmack didn't invent this idea. It was like an academic thing that had been in the academic literature, but he knew about it, and he implemented it in Quake because it turns out it has the same sort of advantages of these quadtrees and octrees, but it's just a bit more suited to kind of maze environments. So the point was that in Quake, instead of having to, like, the maps are quite big, you've got like, thousands of polygons in the environment. He doesn't have to render all the thousands of polygons. He can work out from the tree structure which are the ones that are in the kind of particular room that you're in, and he only draws those ones and only has to collision check against those ones. So it makes it super efficient. In fact, it's probably worth, just for your time, Bsp Trees, just showing you a little bit about that. Binary space partitioning. So this is the basic idea of it, where, so instead of regular grids, it's irregular grids, where you make the grid be based on where your actual polygons are, but you just kind of carve the world up into halves, and you keep going until the individual parts are small. And you can see that I think there's a history down here somewhere where you can see that, yeah. So this work actually started like way back in the day, and more work was done in the 90s and so on. And I think it was about 95 that they started working on Quake, where this technique was used. So this is one of the things that allowed Quake to be fast, which is part of what made Quake a successful game, that it utilised a clever spatial data structure. So now you know about that. So this is basically the trick. You do these things and it lets you be efficient in dealing with large environments. But here's another, lovely dog out there. But here's the other big clincher, right? You have to wait until we stop looking at the dog. You'll have to wait until I stop looking at the dog.
It needs the ladder.
Yeah, he's cute. Okay, so I've told you a couple of big surprises. I've blown your mind with Quadtrees and Octrees, and I've told you about the secret of Bsp trees that made Quake good. Here's an even bigger secret. Sometimes you can just use a big dumb grid. Again, it's amazing how often you get this thing where like there are kind of complex and intricate ways of doing things, and they're good to know, and sometimes they're the right solution. See the number of times it turns out that they end up, the simple thing, it actually turns out to be better. It's remarkable how common it is. So I have direct experience of this. Before I moved to Iceland, when I was working in Scotland on a game called APB, it was based on the Unreal Engine, and Unreal by default uses an Octree, so it does this like clever 8-way dynamic decomposition of the world to try and make collisions fast. But it wasn't fast enough for us. Back then, Unreal really only handled like about 16 players at a time in a multiplayer map. They hadn't done like large MMO scaling yet, and we were trying to do that. So we had to extend Unreal so you could have like hundreds of characters in a single environment, and hundreds of vehicles as well, because we had like a big open city driving game thing. And it just didn't work in Unreal, it was too slow. So I spent quite a lot of time optimizing their Octree implementation. For example, by default in Quake, in Unreal, whenever you move, you know how I showed you that code that did unregister, move, register? That was how Unreal worked, that whenever you moved an object, it would take you out of the Octree, and then it would work out where you were going, and then it would put you back in the Octree. The thing is, often it would put you back in exactly the same place it had just taken you out of, right? So there was a fair amount of computation involved just in like removing things from lists and mucking about with memory and then putting things back in and doing all sorts of checks. It turned out to be completely redundant because 90% of the time you end up going back into the same cell that you came out of. So I did an optimization where we checked for that we kept you in the Octree and we only moved you if you ended up in a different place to where you'd started from, right? And it made it a bit harder because it meant that you had to be careful to not like accidentally collide with yourself, and there were a couple of other special cases. But we did all that to make it faster, and it improved it by a lot, but still not by enough. So then I suggested that the other problem with an Octree is that by its nature, every time you put something in it, you have to do this thing about checking how big the cell is, how many guys are in here. And if it's above a certain limit, you have to split it, and then you have to reallocate all the things. And then if a cell gets too empty, you have to do the other thing. You have to fuse the cells back together. And all that extra logic was taking time. So I suggested, what if we just try not doing that? And instead of having a fancy dynamic Octree, we just use fixed size grids, and we just say the size of the grid is 2 meters by 2 meters. And we just make it a regular thing. We just fill the whole world with cubes that are 2 meters across, and we just keep them that way. And it's like some of them will have quite a lot of people in them, and others won't have many. But the point is, because the grid was very regular and wasn't dynamic, it didn't change in size. I mean, the contents would change, but the sizes wouldn't change. Turned out it's a simpler thing to implement, and it was much faster. So we actually could run our game with a mode switch on it to like whether to use the Octree or the big dumb grid. And we actually ran tests. We get like hundreds of people in playing the game, and it was faster with the big dumb grid, right? Stupid wins sometimes. So that's what we ended up shipping it with. We shipped it in stupid mode because it was faster that way. Now the thing is, Octrees are a good idea, right? But it just depends. It's a case of, like, is the overhead of all that Octree management actually worth it for you? It turned out for us, given the nature of our world, the density of our scenes, the size of our objects, it turned out that it was better to just pick a good size and have a good regular sized grid. Which leads me on to your homework. Right, so you didn't get your homework on Monday because I hadn't told you this stuff yet, and you need to know it because I want you to write a spatial manager. Okay, so we're going to take the entities exercise and add a spatial manager so we can track the positions of the rocks and the bullets and the ships and use that to implement collision checks between them, which was conspicuously missing from last week, right? And when you put collisions in it, it's like that set's nearly done, right? You can actually shoot the rocks and they actually, not only do they detect the hit, but they do what they do in asteroids, which is they split up into 4 other objects. Yeah, you know how asteroids works? I hope you do. When you shoot the asteroid, it breaks up into smaller ones, and you shoot those, it breaks up into even smaller ones. But eventually it stops doing that. It doesn't go infinitely, because that'd be stupid. It does stop. So that's what I want you to do. So for example, when a rock's hit by a bullet, it does this splitting up, and we do it to the point where you get child rocks and grandchild rocks, and that's the smallest one. If you shoot a grandchild rock, it just evaporates. Yeah. So what I could have done for this exercise, and I want you to thank me for this, I could have told you to implement a quadtree, right? Which is like the classical way of doing this. But based on my own experience, it's like, it's not always actually worth it. So, okay, maybe not a quadtree, maybe just put a fixed grid on it, maybe just break the world into like a 2x2 grid. And it's like, nah, 2x2 grid's useless, because if you only log things at the center point and you have to look at the adjacent cells as well, if you only do it by 2x2, you end up having to search all 4 cells anyway, right? So you haven't gained. Okay, maybe I could tell you break it up into 4x4, kind of, but by that point the cells are actually getting small enough that they're kind of the similar size to the objects, and you don't want the cells ever being smaller than the objects because the whole system falls apart when you do that. So I did you a great favour. Rather than making you write a quadtree or even making you write a dumb grid, I'm only requiring you to write the dumbest of all possible grids. It's a grid that's only got 1 cell in it. Because I tried this and it was fine, right? It was like, this is the most stupid spatial manager you can get that is a spatial manager. But for asteroids, it's adequate because there aren't a huge number of things. Now, I was a bit torn because obviously in the real world, you need to do more than this. And I could have said to you, okay, it's not strictly necessary for asteroids, but I want you to do it just so you know. But I didn't want to. I didn't want to force you to do something that's not really useful. So you only have to do 1 big cell. And that makes it quite a lot easier, right? But it's still worth doing, because of like a principle of the thing, the idea that the objects register themselves with a manager, and that manager works out who's colliding with who. That's already an improvement, because remember, up till now, you had the problem where if ever we added a new object to the system, like if I added a new rock or something like that, I'd have to go into the spaceship update code to make the spaceship know about all the rocks so that it knew how to collide with them. You know how we had this thing where the bats and the balls had to know too much about each other, and every time you added something, you had to go and add more collision logic. That's a bad sign, right? It's a bad architecture for a system if whenever you want to make a fairly obvious addition to it, like just adding a new object type to the world, if you have to go in and update all the other objects so that they know about it, you've kind of made a mistake. You don't want that. The cool thing about the entity manager is it breaks that dependency, because now the objects don't have to know about each other. They all just have to know about the entity manager instead. It's like a hub. So each object just says to the entity manager, who am I colliding with? And that way, they just say that and they don't have to change. So if you add a new object to the system, as long as that object registers with the entity manager, all the other objects will be able to collide with it, because they say to the entity manager, who's near me, and it will just give them the answer. So it all works automatically. You sort of understand that it's much more maintainable that way, even though it's like a dumb implementation, it's still useful. So yeah, it's n squared, but it doesn't matter. So the other thing to say about spatial data structures is that in some places there are entire courses on this. In fact, I did find a university where there's a whole, an entire class that is literally just talking about spatial data structures. There's a lot of them. So I've basically given you like the single lecture cram of an entire subject So I hope you appreciate that. That's a semester's worth of information squeezed into your head. So there you go. And finally, the other thing about collision systems is these collision data structures, they can go wrong if people make mistakes, if there's bugs or there are authoring errors. Remember I said that the polygons that you see in a game are not the same as the collision volumes that are used internally. It's obviously like a simplified version of the geometry usually. And there are different ways this can be done. It's sometimes done automatically, or sometimes the level designers actually have to go in and build a low poly version of the map, which is the one that the collision system uses. Sometimes that's how it's done. And sometimes when that's done, it can go wrong. Like there can be kind of slight gaps in the collision model, just little cracks in it, which you can't see because it's not a visual model. It's ideally they should actually have a mode where you can show the collision volume so you could spot this, but sometimes they don't. And you can get artifacts where the collision geometry and the rendering geometry are not quite in sync. You've probably seen this kind of thing, but you can get glitches in collision systems. So here's a little video of someone having a bit of a collision glitch. Okay, so here we've got this wall with what's supposed to be like a solid fence on it, but this is exactly the kind of thing where when you're doing collision geometry, you take shortcuts and you say, I just put like a simplified version of the top part of the fence, and I won't worry too much about the fine details to reduce the poly count on your collision mesh, which is fine until it's not. Sometimes you can end up in little situations where it makes the wrong call as you're moving along the side of it, and you hit one of the collision triangles, and it has to somehow resolve you out of it, and it kind of picks the wrong idea and it pushes you up. Then it pushes you up into a part of the map that you're never supposed to really get to, because it's like you shouldn't be able to get under the rail of that fence because it's too low for you, so you shouldn't ever be able to get underneath it. So there's no point putting the collision geometry inside that because you can't get there except when the collision goes a little bit wonky and you do get there, and then you end up in a part of the map that doesn't have enough collision detail. So you'll see in a second. Right, so you managed to go through the fence, which you shouldn't be able to do, but that's because the vertical bars aren't really there in the collision model at all. And now you're trapped inside a thing that you should have been colliding with, but you're not. And now you're getting to a part of the map that they haven't put the collision geometry in, and you fall through the world. Boom! You ever had that happen? You ever fallen through the world in a game? So one of the reasons it happens is these kind of collision holes or bad collision response, where it tries to move you back to your old position, but it couldn't. There was something else that got in the way, and it had to end up pushing you aside. And in the course of all these pushes, it's actually pushed you below the floor height of the world, and now suddenly you're underneath the geometry. If you're underneath it, you're not colliding with it, but you're on the wrong side of it. So you fall through the world. The other thing that happens when you fall through the world is the world will look very strange. I don't know how much you know about 3D graphics at this point, but when 3D shapes are being drawn, obviously in the real world a polygon would have two sides, right? But you know that in 3D graphics we often only draw one side of a polygon. You do a check to work out whether it's front facing or back facing, and you only ever draw it if it's front facing because the back face is supposed to be the inside that you're not supposed to see. But when if you fall underneath the world, it changes your viewpoint. You're kind of looking up below to the inside of the world, so you can see behind the set, if you like. So you start getting weird things where you're looking at the invisible half of various triangles. So the world starts to look like hollow and really weird. So that's why you've got this weird. Like for example, you can't see the ground, right? You're falling below the ground. You can't see the ground. That's because the ground only gets drawn if you're looking at it from the right side. Because why waste your time drawing it if you were looking at it from a side you're not supposed to get to? But if you do get to that side, you can actually see up through the ground because you're looking at the invisible side of it. So that looks kind of stupid. And also, you're now falling under gravity, probably increasingly high speeds. So this character is like dancing about in thin air, playing animations, while they're accelerating mentally until eventually they get into such a bad position that the system will have to kill them and reset them, which I think is what happens. So yeah, that's what happens when collision goes wrong. Right, I'll stop here because I want to do a second video that talks a bit more about the homework.